So, I'm Nicky Bloor. I'm a managing security consultant at NCC Group. Ex-software developer, done all kinds of software development, desktop, web phones, industrial control systems. I identify as a hacker. I like building stuff to break stuff, solving problems outside of work and techie stuff. I'm a hiker, rock climber. My first year hiking in mountains, I did 70 of the highest English and Welsh peaks. And I am Mixer DB on the internet. So I'm going to start off with show of hands. Raise your hand if you would know what to do if you saw this TCP packet. Okay. So I'm going to start off with a story. I went to a customer site to do a web application assessment. So, yeah, fine with that. Walked up on site and they said, you need a certain version of Java. You need Java 1 point whatever. Like that's a bit strange. It's not really a web app if I need a specific version of Java, is it? So I thought maybe it's a Java client that uses HTTP. So I built a VM. Got that set up, and while I was waiting for the client to provide login credentials for the application, because who cares about prerequisites, started poking around, and I'd have everything set up to proxy through Burp Suite. I could see some requests going back and forth through Burp Suite, great, but I hit login with some dummy credentials on the application, nothing went through Burp Suite. Did it a few more times, and the application said something about being locked out. So obviously something wasn't going through Burp Suite. So I fired up Wireshark. See what was going on. Yeah, so each login attempt that I created, that I did with the application, resulted in a packet similar to the one that I just showed you. So it was actually a Java application served over HTTP. So it was a Java website application, not really much in the way of a web app. So that packet led to the discovery of a vulnerability that had survived multiple previous assessments. The vulnerability gave me a foothold on a server that had been, like I said, been tested before from an external perspective. Had a pretty hard shell, but soft interior. I ended up rooting, I think I've got an extra slide in there. Ended up rooting basically the entire environment within minutes of finding this vulnerability. So it was a serialization issue, and honestly, I would have missed that vulnerability myself. But I've done quite a bit of research recently, playing around with stuff related to deserialization and the kind of vulnerabilities and attacks and issues there. So as soon as I saw that packet, I recognised the format of the data, knew what to do straight away. I knew what the risks were. I've done that much research in this area. I can read the raw hex dumps of serialized data because I've had to do debugging my own code. So yeah, I'm here to talk about serialization attacks and hopefully make them a bit more practical to execute. Yeah, the first thing that I should probably say about this is that practical isn't necessarily point and click. Attacks against serialization issues are generally a bit more involved than attacks against other common vulnerability classes. You could think about it as sort of like manual SQL injection. So sometimes you can just fire SQL map against a request and it'll dump the database for you. Sometimes it's a bit more involved and you have to work out where you are in a query, what the kind of query it is, and how to exfiltrate data. So it's a bit more involved. Serialization attacks are rewarding. They often lead to remote command execution. So it's important to know how the attacks work, how serialization works, in order to attack it effectively. So we're going to start off with a bit of technical background. Briefly, serialization is the process of converting runtime program data and objects and variables into a format that can be stored or transmitted. The reverse process, deserialization, converts records on disk or data that's come over the network back into runtime objects and variables. The more complex the runtime data structures are, so in object-oriented languages we can have nested objects and so on. The more complex the serialization process and format must be to cater for all possibilities. And then, as a result, there's more scope for things to go wrong or for the functionality to be abused. And there is no fixed format for serialized data. Developers can use any serialization method they want. So just common examples are JSON, XML, just complete custom format, could just write binary data out to a file. But higher level languages tend to have a built-in serialization mechanism and format. So Java, Python, PHP, they all have their own serialization mechanisms and formats. We're focusing on Java serialization for this talk. But the sort of high-level concepts and the way that you attack serialization, it tends to it applies to other technologies. So PHP, for example. So Java's built-in serialization. It's easy to use. So to mark a class in your program as serializable, you implement the java.io.serializable interface. You can then use java.io.objectOutputStream to serialize that object, or serialize objects of that class. And it's just a case of calling the write object method, and that'll write that data out down whatever stream you want. So whether it's a file output stream or a stream that's right into a network packet. And then java.io.objectInputStream does the reverse and does the deserialization. But like I say, it's easy to use. All you have to do is implement serializable and then write the file out, write the object out, read it back in. The actual data format can be described as a simple stream format. So it's just a stream of bytes. You start off with a magic number, ACED, hex, and that's followed by a version number, 2 bytes, which I've never seen anything other than 0005. I'm sure there is an older version, but that's all I've seen. And then following that, there is at least one content element. And content element is, so there are various types of content elements, but they're all described by the first byte, which tells you the type of the content element. So null is just the byte hex70. An object begins with a byte hex73, and then an object will actually have additional data following it in the stream. So that first byte tells you the format of the data that's going to follow in the stream. The serialization specification is available online through Oracle, but it's a bit unclear in places, and when I've been parsing it, it's not been exactly as it sounded like it should be. So I've got some examples of some Java serialization. It's just to give you an idea of what the data looks like. So this is a minimal stream. We've got ACED followed by 0005, and then the first content element and the only content element, which is 70, which is a null. element. That's a minimal stream. You need to have at least 5 bytes. Second one is a string, which is just 4 A's. So byte 5 is hex 74. That tells us it's a string. The following 2 bytes then are the length of the string, and then following bytes are the actual string contents. And then we've got an object, and this is literally that code there, class simple objects, implements serializable. There's no fields or anything, so that's just an object. We see byte 5 is hex 73, and then following that, hex 72 is a class description. So we have the class name, and then things like serial version, UID, number of fields, some flags, and then it finishes up with so objects can be, classes can be annotated. So 7.8 tells us there's no annotations there. 7.0 is the superclass description. There is no superclass. So, like I said before, java.io.objectInputStream does deserialization in Java. Serialization data stream is passed sequentially. Each byte is passed and turned into objects and data in memory. Objects that are read from the stream are instantiated immediately. And there's little validation, possibly no validation, really. It's so in terms of validation, the stream format's not correct, so the content type byte isn't a valid content type, then it won't process it because it doesn't know how to. But Java, the object input stream basically passes the data that you pass to it in accordance to the format, the stream format, and then it relies on code wherever to throw exceptions if there's an issue. So, for example, if we read an object from a stream, object input stream ois.readObject, and then try to cast that to a string, if that object isn't actually a string, there'll be an exception thrown there. But by the time that exception gets thrown, the object input stream has already instantiated that object in memory. It's already deserialized. It's become an object in program memory. So in order for a class to be serializable, we need to implement java.io.serializable. If we implement that interface, we can have a readObject method as part of our class, and that allows classes to read additional data. There's also a writeObject method that allows you to write additional data out to the stream. And it can also, so it can be used in conjunction with Java's default method of reading serialized data. It can also handle the objects loaded event. So it gets called when that object is being read out from the stream. So you can use the object input stream's default readObject method to read the object into memory, and then you can do some additional processing. So, for example, if you've got a class that handles, that manages your database connection, you might have properties to connect to the database that class might have properties to connect to the database. So when you save that out, those were written out to a stream, to a file. When you load that back up, you might want to handle the sort of object loaded event to reconnect to the database. So you can do that in that method. So deserialization vulnerabilities occur when an attacker controls the data that's being deserialized. The deserialization allows us to control the properties of the object that's being deserialized, or even to control the type of the object that's being deserialized and instantiated. And by controlling the data, we control the flow of code which uses that data. So that includes things like the code in readObject that handles the object loaded event. So in that example with the database, we could have the the application connects to a different database server potentially. And we also control code that interacts with the object after it has been loaded. So if I instantiate an object input stream, call read objects to load something from a file or from the network, and then I interact with that object, that code can be controlled. So exploitation of deserialization vulnerabilities is known as property-oriented programming, because we control the properties of the class or the object, and we use that to influence the flow of code execution. A payload consists of one or more objects with properties configured to control the flow of some existing code. And this is the main reason that it's difficult to exploit deserialization vulnerabilities. The code has to exist already as part of the application. We can't supply our own code for the application to execute. So the code that we do control is known as a pop gadget, and it's basically a high-level ROP gadget. So instead of pushing a value onto the stack or setting the value of a register, we're doing things like writing data to a file or renaming a file. Similar to ROP gadgets, you often need multiple gadgets chained together to do something useful. So exploitation relies on knowledge of the source code. We need to know what the code does to be able to manipulate it. But unfortunately, it's not always possible to obtain the source code. You don't always have it available. So how do we attack serialization vulnerabilities without source code? Third-party libraries. Here's some common examples. And then the tool Serial, something you might have heard of. Serial has it can generate pop gadget chains for all of these libraries and more. And these are basically objects that are already. It sets up the properties of the object such that when that object is instantiated, some useful payload executes. And most of the payloads allow us to execute arbitrary operating system commands. And it's these payloads that we're going to focus on for this talk, because I'm trying to make it practical, easy to exploit. And most of them are blind command execution payloads. So, covered off some of the background information there. Let's look at the actual process of performing an attack against Java serialization. There are three key parts to an attack. The first bit is we need an entry point. We need to be able to provide data to the application that's going to be deserialized. Then we need some pop gadgets that we can control to do something useful. And as I said, we're focusing on command execution gadgets. So we need some payload commands that will allow us to do something useful with the server or the target. An entry point is any part of the application that deserializes data. To identify those, we want to look for the serialization header. To get a stronger indication, that followed by a content type byte. They range from hex 70 to hex 7e. So, for example, we've got a HTTP request here, which clearly has some raw binary data in there. If we look at the hex view, we can see ACED 000573. So we've got a serialized object in there. Again, Wireshark, we've got a TCP stream. Starts off with serialization header and 7.3 telling us there's an object in there. Text-based protocols and formats, HTTP, XML, so on, are more likely to use to encode the data because it's binary data. It's not compatible with text formats. So they're likely to base64 encode that data. This still creates patterns that we can recognise to identify an entry point. So, for example, all serialized objects, because that header will start off with the string R0AB if the base64 encoded. So there are other indicators that we can use to identify Java serialization. If we look at the data in a text or ASCII view, then there are various strings that will stand out. So the obvious one there is Java class names. Got a couple there, java.lang.object, a few there, com.foo. They're examples. You can see them highlighted there anyway. In some places, the class names use a different format. It's just part of it's down to the protocol, the stream format, specification. So instead of com.foo.a, this other format begins with a capital L, then the class name, which is the namespace and class name sections are separated by a slash instead of a dot, and ends with a semicolon. So there's some examples of that. Now the other indicator is that there are, due to the stream format, they will appear in the stream. So we've got SR there, which is a object followed by a class definition. You can have different combinations, but that will always be in the stream somewhere if there is an object in the stream. And then XP, which appears if a class has no annotations and no superclass. So again, that's something that will appear quite commonly. So I think here we've got there's another example later where there's a java.lang.short in the stream, and the superclass java.lang.number doesn't have a superclass, so you see the byte 7870. So that login packet, and I've deleted the image off of it. That login packet can be full. There are several indicators that I'm going to get that image back because it's kind of important. I don't know why that's not displaying. I can see it on the slide. Okay, well, PowerPoint's not playing ball, but there are all of these indicators in that login packet. We have the class names in both formats, I think. We have the strings SR, XP. For some reason, PowerPoint is just not playing. But the thing with that login packet is it was missing this bit, and that bit is, well, a lot of people rely on that to identify Java serialization data. And there's actually intrusion detection systems that look for that combination of bytes to detect Java serialization attacks being traversing the network. And they wouldn't have found the attack that I performed using that login packet, because those bytes only appear right at the very start of any serialization stream. So the application that I was attacking in this case, when it initially established a connection to the server, the serialization header went over the network. It was various other packets going back and forth, but when I saw the login packet that went over, just began with 7.3, an object. And that's because, like I say, those bytes only appear at the beginning of the stream. So the payload was undetected by the intrusion detection system. So don't rely on that header being there, is the point. So these other indicators that tell you that we've got serialization data, they're a better indicator.
There it is.
There it is. So we've got an entry point. The next thing that we need to attack serialization issues is pop gadgets. They weren't meant to be animated. So to find gadgets, we need to review application source code. We're looking for classes that implement the interface java.io.serializable, and also implement a read object method. If that read object method does anything of interest with the properties of the class, or just generally, if it does anything of interest, then we can use that method as a pop gadget, essentially. And similarly, if we find instances in the code where java.io.objectInputStream is used to read objects from a serialization stream, any code that works with that object after it's been read from the stream is potentially a gadget. So I'm talking about practical serialization attacks. Like I said, you're not always going to have access to source code. So we're going to stick to known gadgets. Gadgets in common libraries. But how do we know what gadgets to use, what gadgets are available? The first protocol is, it should be background information about the application that you're testing. If you can ask someone, or if you've got access to the application, you can see what jar files are there, you can see what libraries are being used. There might be an information disclosure issue that will give you a bit of additional information. But if all else fails, kitchen sink it. So throw everything but the kitchen sink at it, and the kitchen sink. So if we know what libraries are available to the application, then we know what gadget chains we can use to attack the application. So this is a partial mapping of jar file names to YSL serial pop gadget chains. Something to note here is that there's a lot more pop gadget chains in YSL serial for example, Commons collections, and there are other pop gadget chains in there that have sort of interdependencies. So Commons bean utils depends on Commons, an old version of Commons collections being there. So there's no point in that library being in there. Yeah, that exploit, there's no point in testing that exploit. Test the Commons collections one. So kitchen sinking. This bit of Python code basically brute forces through the YSL serial command execution payloads all of those payloads allow you to execute. So there are some other types of payloads in YSL Serial. All these ones allow you to execute arbitrary commands. And all it does is loop through the different payloads. It uses subprocess to check output to generate the payload bytes using YSL Serial. And then it passes the payload bytes to a fire payload function. So essentially we're brute forcing available pop gadgets. It's noisy. It might not be a problem always, but it's noisy. And the other issue is that we're blindly attacking the application. So we just fire all of these payloads off at it. One of them might work, none of them might work, but we don't know which one actually works. We also don't know necessarily what commands are available in the target environment. And we also might end up running a command multiple times, which could be problematic depending on what commands you're using. So ideally we want to get some feedback from the application. Most environments have the ping command available, so you could try pinging your own IP, monitoring the network traffic to verify that the payload command was executed. If a ping came back and hit your IP, obviously that command was executed, and that pop gadget chain worked. If you do that, limit the ping count. I was putting together some of these scripts and doing one of these attacks and completely forgot to put the -c in there and ended up with a server with, I think it was about 10-15 ping processes just hammering my box. The other thing that we can look at doing is to use an invalid command. So we just provide a random string that isn't a command that's going to be available on a server. We might get an exception back from the application. If that pop gadget chain was successful, then java.lang.runtime will throw an exception, and that'll be an IO exception saying that it cannot run that program. The program doesn't exist, so it can't run it. Alternatively, if a class not found exception is returned by the application, then one of the classes that's included in that pop gadget chain wasn't found, so that library and that chain aren't available to the application, which is no use. So back to this, we've got an entry point, we've got a pop gadget chain. The final part is we need payload commands that we can execute. We want to turn blind RCE ideally into a shell that will allow us to observe command output, and we can use that then to gain further access to the server or environment that we're attacking. Again, we can use the kitchen sink approach and blindly fire commands at the target until something works. Again, that's noisy, not really ideal unless you're testing against a test or development environment. What we can do instead actually is using the same trick that I just mentioned with the invalid command and look at the exceptions that come back from the server. So, yeah, we get an IO exception saying cannot run program, then that command's not available, obviously. So, there are limitations to java.lang.runtime.exec. The YSL serial command execution payloads aim to get to this method and execute this method. That's how you get command execution. The gadgets set things up to be able to instantiate, to be able to call this method with an arbitrary string. And there are limitations to that. So the first one is that we can pass parameters to a command, but those parameters themselves cannot contain whitespace, because runtime.exec with a single string parameter splits that string based on whitespace, and the first element will be the command that it tries to execute. Subsequent elements will be the parameters. So in this case, I've highlighted, excuse me, the different parts that we get when we try this command. Different colours, different parameters. In this case, second example, we end up with essentially the same as running the dir command with 3 separate arguments, or 4. So it'll attempt to do a dir of double quote C documents, and then a dir of and. So the other limitation is that there are there's no support for sort of shell operators, so piping output from one command into another command, output redirection, so for example echo to a file to write a shell. There's no support for that. There is a workaround for that under sort of Unix, Linux environments, but I'm not going to talk about that here. So, some examples of typical payload commands that we might use. We've confirmed a gadget chain is usable. We might run a typical netcat shell. If we don't manage to, if we can't execute a netcat shell, we might try and download a shell and execute that. And if we're going to try and download a shell and execute that, it's also worth testing for the presence of interpreters, such as Perl and Python. Under Windows, we might try setting up a file share, and then just doing a copy command to copy a shell binary onto the server. That's got a bonus side effect that we can capture the hashes from the server. If PowerShell is available, though, we've got that's ridiculously powerful. We can pass a basic Explorer encoded PowerShell command or script to PowerShell on the command line. So that is equivalent to invoke web request to download a file from over the web. What we can do to identify those commands, we can basically just run the command without a parameter, and look for the exceptions that come back to identify what's available in the environment. So we've now got everything that we need to execute a serialization attack. So I'm going to look at some examples now of real attacks and real vulnerabilities. So first one, Spring HTTP remoting. Anyone familiar with Spring framework? So the HTTP remoting component allows a developer to expose any Java class over HTTP. And there's no effort involved in doing so. I think maybe a line in an XML configuration file. And Spring does a lot of magic behind the scenes, and it makes that happen. So that's facilitated by the Spring Framework remote invocation class. And so when a client application uses Spring HTTP remoting to interact with a remote class or remote object, Spring Framework does some reflection magic in the background and constructs a remote invocation object. It then sends that object to the server in the body of a HTTP post request. On the server side, the remote invocation object is then used to identify the target object and call methods on it. And that's how it posts this request, this object to the server. Java serialization. So that's the entry point. If you've got an application that's using Spring HTTP remoting, you can just you post an object to the server. So we can add a few lines of code to that Python script that I briefly mentioned earlier, and we can brute force through the different WISO serial payloads. The highlighted line is just a single line that makes a post request and puts a payload in there. And when the response comes back from the application, we check here if there is a class not found exception in the response. If we see that, then the pop gadget chain isn't any use to us. If that's not there, it's potentially usable. And if the application has any known gadget chains available, then we'll get RCE. But this shouldn't happen. Applications that deserialize data should validate that the type of the data that they're deserializing is what the application expects. So in this case, Spring Framework expects a remote invocation object, and the payload in this case supplied a java.util.hashset object, which is no way compatible with remote invocation. So it's not done any validation there. But as I mentioned before, Java and serialization relies on some exception being thrown to stop serialization if something's not right. So this object gets deserialized, it gets instantiated in memory, it then gets cast to a remote invocation object, and that fails because the classes aren't compatible. And that happens, it's Spring Framework that's doing this. So this happens after the payload object has been deserialized and executed, but it happens before Spring Framework passes this object to the application itself, the application that uses Spring Framework. But according to Pivotal, who makes Spring Framework, this is an application issue and not an issue with Spring Framework. They refuse to fix the issue, despite one of the security team actually having a CVE for a very, very similar vulnerability in JBus. And it was actually this member of their security team that I reported this to. Whatever. So, next example, one of these big, expensive enterprise applications that's not readily available to just anyone, because it costs millions or whatever. You've got to pay for consultancy to roll it out and integrate it. Obviously, it's not called Acme Money. It's likely to be encountered on large internal networks. So that login packet, and it is going to pop up. This application is where I actually encountered that login packet. And this is obviously our entry point in this instance. So we've identified serialized data. We can provide some data to the application to have it deserialize it. The exploitation in this case was a little bit more involved. Still very easy. So after I spotted serialization data, I closed the application down, because if we go back to that, like I say, the stream doesn't begin with the bytes A, C, E, D, so on. So I wanted to find out what was going on. So I closed the application down, I started a fresh packet capture, and I relaunched the application and made another login attempt. So I followed the stream in Wireshark, and that showed me everything that I need. So first we've got the serialization header being sent to the server, followed by a few bytes, and that's the start of the stream. After that, we've got two packets that come back from the server. So we've got the serialization header being returned, because there's an input serialization stream and there's an output serialization stream. And then finally, we've got a serialized object, and this is actually sent to the server before that login packet. The key thing is there's a hex 73 there, which tells us it's an object, so we can inject any object we want into that stream now. So again, we can take that script from before that brute forces through, and we just change the fire payload method, and that allows us to enumerate and attack the service. So we replay that first packet. Every time I did one of these packet captures, that packet was static, so this was a nice easy one to attack. So we replay that first packet when we connect to the server. We receive the two packets that the server sends back, and then we send the payload to the server. The server deserializes it. That's our entry point. The reason for those that don't know Python or might not have clocked, that the 4: in square brackets after the P is our payload. 4: is just because that serialization header has already been sent. So when we generate a payload with YSL serial, we'll get the full let included in the header. So the 4: just scripts off that header and sends the rest of the data in that packet. So similar to before with Spring Framework, I found that the underlying application doesn't care if I send a java.util.hash set instead of, in this case, it was a java.lang.short. Didn't care that I sent a hash set instead, so it wasn't doing any validation. And so I did an enumeration run, found out it was using an outdated commons collections library. And yeah, with that I've got command execution. So I've got the server to ping me. So at this point we've got code execution, command execution, unauthenticated, remote command execution, and we've basically won. But I'm going to take this example a little bit further because I think it was a full gig, and I think it was a good example of what can be achieved by just putting a little bit of extra effort in and attacking one of these issues. So, verify command execution. I wanted a shell on the box. Went for the usual suspects, and the server didn't actually have any of these commands available. So I was trying to enumerate what commands were available, and while I was doing that, I found that Perl was available. And you can pass a Perl script to Perl on the command line and execute it. The problem is, to do anything with sockets, you need use sockets with a space in between. So I couldn't pass that in, I couldn't use Perl in this case. But I ended up, I spotted the TFTP command on there that was available on the server. And there's a nice little Python library that allowed me to just do a quick, dead easy TFTP server on my box, and that gave me access to the file system on the server and allowed me to download files from the server and upload a Perl reverse shell. It turns out it was a AIX box, which is actually the only one that I've ever encountered. So I've got a low privilege shell at this point. One more. So I was in luck because operating system updates aren't important, obviously. So there was a known local privilege escalation for this version of AIX, except that the published exploit was written in C, and the build tools and libraries to build the exploit on the box weren't available. I wasn't about to mess about cross-compiling and stuff. I ended up rewriting the exploit in Perl. Painful. But it was worth it because I got root. And then from this box, I was able to jump around the entire environment. I was in the sort of test dev environment to do the assessment, and I jumped across to the production environment, which set off alerts because somebody logged into that box, and all the sysadmins were panicking. And I jumped across multiple data centers, and it took about half an hour from seeing that packet to taking the whole environment. So, raise your hand now if you feel more capable of attacking Java serialization issues. A few of you, okay. Well, I've gone over all the gory details, but I'm about to make it a little bit more practical. So this morning, I had a battle with the internet, and I managed to get onto GitHub eventually and release a script that basically automates everything that I've talked about. So it handles brute forcing through the different pop gadget chains. It can deliver payloads. So there's two versions. This one can deliver payloads by replaying TCP streams, or by replaying HTTP requests and injecting a payload at a given location. So it can exploit both the examples I talked about. It also looks at response data from the target application or the target server and looks for those exceptions that tell us a bit more about what's going on. So if there's a class not found exception, that gadget chain isn't usable. So it'll tell us that. And it'll tell us if there's, if the command's invalid that we attempt to execute. It can do the, gadget detection by using a string that's unlikely to be a valid command and brute forcing through and telling us which ones are valid. I've thrown the script together last minute, so and it's not intended to be a robust attack tool that's going to do everything for you. There's loads of situations it can't handle. So, for example, if the first packet in that Acme example had a session identifier that has to go out in subsequent packets, then it wouldn't pick that up and pass it out. The idea is that it's an example and something that can be used as a sort of baseline and be tweaked to attack average applications, but you need to put in a bit of effort to work out what's the protocol up to the point you can deliver an object. Having said that, if you do use it and there are any bugs or things that I could improve, do let me know. So there's also a cut down version of the script with a dispatch payload method, and this version of the script you can just put your own payload delivery code into there. So it might be send a packet, receive 2 packets, send another packet with the payload, and that's sort of a skeleton that's a starting point for writing for an exploit. So, conclusion, exploitation of serialization attacks is typically a bit more involved when you've got to do things like looking at Wireshark for the packets and the communication protocol. It's important to understand how the vulnerabilities work and what's going on behind the scenes on the hood to actually execute these attacks effectively. Exploitation is rewarding, routing multiple servers. This kind of stuff seems to be hidden in lots of sort of big, expensive enterprise applications. These kind of applications aren't readily available. There's no trial versions, and they are likely under less scrutiny from people like us. So there's also a better chance that it's vulnerable, probably in other ways as well. And that's that. I've got some useful resources there, but any questions?
So you know, when you use this brute force application, can it crash the application on the server? So is it wise to use it on a live system?
Unlikely. So Java, well, it's just there's just exceptions being thrown. The worst that I've seen happening is that the exception is actually returned to you, so you can do enumeration and you can see that gadget chain isn't available or command isn't available. Yeah.
So it's not going to kill the server.
Would it be possible, if you were really masochistic and hated yourself, to actually make the object download the stager code itself from the Java?
Yes.
Yeah, okay. So you don't have to worry about FTP or anything on the command. So you wouldn't have to worry about using any external command line tools to pull in things?
Yes, yeah. Provided the right gadget chains are available to the server, yeah, you can. So a lot of the WISL serial gadget chains basically instantiate a class, so they have a class in bytecode that calls java.runtime.exec, and they instantiate that in memory, and so you can change that to anything that you want, essentially. Any others?
Did you look at using the MS-DOS file path to get around the file path through spaces?
No. The attack, the sort of Acme attack that I talked about, that situation, that was in a AIX environment. So I was just not MS-DOS. Any other questions? Thank you very much for attending.